Okay, so this is the first problem for internal flow, and I have discussed different theories for internal flow, like the average velocity, temperature velocity, entrance radius, fully developed flow, the thermal considerations. So now we'll start solving this problem. So this is the first problem. Is system for heating water from an inlet temperature which is given 25 degrees centigrade to an outlet temperature is 70. It involves passing the water through a thick walled tube having inner and the outer diameter is 25 and 45. The outer surface of the tube is well insulated. So look here, so the outer surface of the tube is insulated. So keep in mind this information. Look here, this outer surface, this is insulated. So because it actually wants to prevent the heat transfer. And the electrical heating within the wall provides for a uniform generation rate is this. So this is actually the heat generation here. You see this is given 1.5 10 to the power 6. This question has two parts. We need to calculate the length. So see here, how for a water mass flow rate days, how long must be the tube be to achieve the desired outlet temperature? So the outlet temperature, it is 70 degrees centigrade. So to get this 70 degrees centigrade, how long you need to ensure that the length of your tube, the tube. So that means how long must be the tube to be achieved the desired outlet temperature 70 degrees centigrade. So this how long means we need to actually calculate the length. So from this entrance, this entry length, so this is actually the inlet and this is the outlet. So what actually how much length we need to achieve this temperature 70 degrees centigrade. And the second question is, if the inner surface temperature is 110 at the outlet, so inner surface temperature, that means this is the inner surface and this is the outer surface of this tube. So at this inner surface, this temperature is 110. So what is the local convection heat transfer coefficient? So you need to calculate the H(x), the convection heat transfer coefficient. So at first we'll start with the first section, that means we'll calculate the length. So before going to solve this problem, let's have a look at this figure. You see this schematic here. This is actually the X inlet, this is the X directions, right? This is the outlet. So we have this pipe here. Actually the outer surface is insulated, so adiabatic condition there. So from this section to this section, you see this is actually the inner surface of the tube. So this is the inner diameter, and if I draw this line like this, so this is actually the outlet, the outer surface. So this diameter is given 45. The water is the material here. So water is flowing this direction. You see this arrow, it is 0.12 kg per second, right? And we have the the uniform heat generation. This is given 1.5 and 10 to the power 6. So this is all of the information we know from this problem. So we need to, the first thing is we need to calculate this length L. So let's start with the solution now. So I told you initially, keep this information in your mind. The outer surface is insulated, and so we need some assumptions, because we need to make this question simple to avoid the calculations, the complex calculation procedures, and sometimes it is not possible to consider all the aspects of the problem. So we usually make some assumptions to make the problem simple. So let's say the assumptions here. So definitely this is a steady operating conditions. So you already know for most of the problem we are using these assumptions. So we have uniform heat flask. We have the constant properties. So that's the assumption is that the constant properties. And the outer surface, this is this is insulated. So this is the adiabatic outer surface, and we say is the incompressible liquid and the negligible viscous dissipation. So that's all our assumptions for this problem. So once we have done with these assumptions, then we'll start with solving the problem. So if you look here, actually we don't know, actually it is not given any water properties. So we only know the pipe specification. So we know the mass flow rate and we know the heat generation rate. That's it. But we don't know any properties for water. So we will calculate the bulk mean temperature at first. So if you see here, the inlet temperature is given 25 degrees centigrade. So we say this is the inlet temperature and the outlet temperature is given 70. So the bulk mean temperature, it should be 25 plus 70 over 2. So this is 47.5, that means 320. So now the important thing here is we actually need to calculate the length L, and I will show you the equations how to calculate that length L. So the thing is, since the outer surface of the tube is adiabatic, it is well insulated. So that means the rate which is generated within the tube wall. So like we have this pipe, we have the inner surface, outer surface. So the rate at which the energy is generated at the tube wall, must be equal to the rate at which it is convected to the water. So that's actually the important thing here. So we can say, if it is true, we said you see, the outer surface of the tube is adiabatic, so rate at which the energy is generated within the tube wall must be equal to the rate at which it is convected to the water. So that means Q equal easy, that means Q equal easy, that's the heat generations, which is equal to the rate of heat transfer due to the convection to the water. So we need to calculate the rate of heat transfer Q. So in a different formula, so far you calculated the rate of heat transfer due to conduction, due to convections. So for convection, maybe you're familiar with the formula, which is Newton's law of cooling, Q equal H A delta T. So this is related to the heat transfer coefficient H. So Q equal H A delta T. But for this problem, actually we know the mass flow rate at the inlet. So when we know the mass flow rate, so that's easy. We know the inlet temperature, we know the outlet temperature. So that means we know the delta T, the temperature difference, and we know the mass flow rate. So when we know that, then the thing is, there is the other formula to calculate the rate of heat transfer, which is Q equal M Cv delta T. That means the mass flow rate, specific heat, and the temperature difference. So if you see here, we don't know the specific heat. So that means we calculated this bulk mean temperature, and by using this temperature, now we can calculate the Cv. So okay, definitely we need Cv to calculate the mass flow rate. So as I said, we'll do some kind of the energy balance here. So this is Q equal actually the rate at which heat is generated at the wall, and it is the heat transfer due to the convection. They should be equal. So we can write like this. So if you see here, we can actually write like this: Q equal QV. This is actually the rate of heat generations, and this is the volume. So if we multiply the rate of heat generations with the volume of the tube, then we'll get the rate of heat transfer. So this Q, it is actually given, and the volume of the hollow section, the hollow tube, it is pi d square and L. So actually d means we actually need, this is the volume of the hollow tube, so that means the outer diameter minus the inner diameter. So the outer diameter is 45, this is the inner diameter, so we are getting that hollow section. So that means Q equal Q into pi d square L and over 4. That's the formula actually, pi d square L over 4. So that's we got the rate of heat transfer. And we decide the other thing is Q equal mCp delta T. So So now from equation on what we can write, you see we can write the mcp delta T, this is equal this. So this is actually the rate of heat transfer. This is also the rate of heat transfer because we know the mass flow rate, and by using the mass flow rate we can write it as mcp delta T, and you know delta T equals T naught and Ti. So at first we will calculate this, then we will calculate this. So why we are using this formula here? So that is the main thing actually. We need this length. If you see here, when we calculated the mass flow rate by using this formula, the rate of heat generations and the volume of the flow tube, then we got this length from the formula. We actually need the length L, and this is actually the first section of this question. We need the length L. So if you see here, so this is also the rate of heat transfer, this is also the rate of heat transfer. So if we say okay, this equal this, according to that principle, the energy conservation principle, if we say that this equal this, then we know the mass flow rate, we know the specific heat, we will calculate the specific heat from this bulk mean temperature. So if you want, then you can do it at the very beginning. So then you know all of this, then you will get L. So let's calculate the rate of heat transfer by using this formula at first. So when it is the case, we know this mass flow rate is 0.12, we know the temperature difference delta T, but we don't know specific heat. So at 320.5 Kelvin temperature from the table, we got the specific heat is this 4177.25. So now substitute all of these values in this equation 3, and then we'll get Q. Okay, so you see here we substituted all of these values, and then we got the rate of heat transfer is 22.557 kilowatt. So that's we got from there. And now again we will calculate from equation 2. If you can remember, it is Q pi d naught square di square L. So this is actually the rate of heat transfer. We got it from this formula from the mass flow rate. So let's substitute that. This is the the heat generation rate. This is the constant phi. D naught equal this. We converted it into meter. It is in millimeter. This is di. We don't know this L, and this is from the formula. So now if we simplify this, definitely we will get L. So this is the first part of this problem. So we got the length here, it is 13.67 meter. So that's actually the length we need to achieve that outlet temperature, which is 70 degrees centigrade. So this is the first part of this problem. So now we will start with the second part of this problem. If you can remember, the second part of this problem is, if the inner surface temperature it is 110 at the outlet, what is the local convection heat transfer coefficient at outlet? So let's solve this part. So this is actually this is the section B. So if we need to calculate the local convection heat transfer coefficients, the convection heat transfer coefficients, you definitely need to use the Newton's law of cooling. So which is Q equal H A delta T. So H equal Q A delta T. So you can easily calculate the area, you know the temperature difference, and what about this Q? You know this. So let's calculate the area at first. So this is a very simple formula. So by DIL. Now if you have any question why I'm using DI, why not D naught? So we have the inner diameter, we have the outer diameter, so why I'm using DI? So look, just read the question carefully. It says if the inner surface temperature of the tube is this, what is the local convection heat transfer coefficients at the outlet? So you know the inner surface temperature here, and you need to calculate the local heat transfer coefficients for that temperature. So that's why we're using actually this one. We're not considering this outer diameter. So As we're dealing with the inner surface, so we are using the inner diameter. So this is 0.025. So meter, definitely in meters. So I didn't write the units here. So this is pi di, and we already got the length here, 13.7. We just calculated that length. So this is actually the area, internal surface area of the tube. So now we know this area, we know delta T, we know Q. So just substitute all of this value here, simplify it, and then it will get to heat transfer coefficient. Alright, so now let's substitute all of this value. This Q we already calculated at the very beginning, so this is 22.557. We know A, we know the temperature difference, so we got this value is this. So that means the local convection heat transfer coefficient of the outlet is 0.525. So that's it. So what I did for this problem is it was quite simple. So initially, we calculated we just write down the assumptions. Then we calculated the bulk mean temperature. We said as the outer surface is insulated, so that means the outer surface is in adiabatic conditions, and the rate at which heat is generated of the tube wall, it should be equal to the rate at which it is transferring the heat to the water by convection. So then we calculated the rate of heat transfer by using the mass flow rate. So this is mcp delta T, Q we call mcp delta T, and the other formula, as we need the length L, so we calculated the other formula like this, the rate of heat generation Q, and this is actually the volume of the hollow section. So by using this, we got this rate of heat transfer. Eventually we got this length L. So it was our ultimate target, so that's why we used that formula. And then we did some the energy conservation, like this heat transfer equal this, because this is the steady conditions. So we wrote this equal this, and then we got the length L. So once we got the length L, then we need the local convection heat transfer coefficient. So what I did, we used here the Newton's law of cooling. So Q equal H delta T. When it is Newton's law of cooling, this is actually, we need haze, so that means we need to use the Newton's law of cooling. And then we calculated the area. Once we calculated the area, then we know the other thing like the temperature difference and the rate of heat transfer. Then we substitute this, we got it. So that's actually the solution of this problem.